Hey everybody. Hopefully you've watched my introduction video, but just in case you haven't, I'm Josh Jordan, and I'll be talking to you about non-Kähler Calabi-Yau geometry and Pluriclosed flow. This is joint work with Mario Garcia Fernandez and Jeff Streets. So, I guess kind of the place to start is with some background. Okay, I'm planning on talking a little bit about Hermitian geometry, a little bit about Bismut-flat structures, and then moving on to holomorphic Courant algebroids, which are really the setting for most of the work we do in this paper. So let's start with some background. In terms of Hermitian geometry, at least for this talk, right, I'm trying to presume that people know Riemannian geometry, at least the definitions, but I'm trying to give as much of the Hermitian geometry as I can. Okay. So the place to start is pretty much always the metric, right? And we deal with specific kinds of metrics. So first off, if you have a complex manifold equipped with Riemannian metric, right? So MJG, J is the complex structure, square is the -1. It's integrable, all of that jazz. We make the following definitions. So we call G Hermitian if J is a G orthogonal endomorphism of the tangent bundle. Using the fact that J is G Hermitian and the fact that J squares to -1, well, negative the identity, we can define this real 1-1 form that we call the Kähler form. Okay, this is typically denoted by omega, and then just so we're all squaring up our conventions, I usually put J on the first index, but that's just me. Everybody uses a slightly different one. G and J are called pluriclosed if I del bar of omega is 0. Sometimes you'll see this written in terms of real operators as d dc of omega is 0. Yeah, and typically speaking, we kind of abuse notation and treat G and omega on the same footing. So we call both pluriclosed, really. Something to notice is that the pluriclosed condition is strictly weaker than the Kähler condition. All right, so if you haven't seen much complex geometry, the Kähler condition is this particular integrability condition, d omega equals 0. All right, this is strictly weaker. There are examples like Hopf surfaces, which we'll talk more about, that are not symplectic, so they can't be Kähler. Okay, d omega is not 0. All right, Godesham proved that every complex manifold admits a certain kind of metric with an integrability condition that is more general than the pluriclosed condition, but in the case where n is 2, right, this m2n, when n is 2, this reduces to the pluriclosed condition. So every compact complex surface admits a Godesham metric. And omega here, right, this 1-1 form, defines two relevant cohomological quantities for us. The first is, it's called an Epley class. I don't want to get too into the definitions, but basically, they're 1-1 Epley classes if IDD bar vanishes. Okay, omega also defines this thing called the torsion class, right, del omega. It's related to the torsion of the Chern connection, and it's a Dolbeault class, which is important. Okay, so del bar of del omega vanishes. Now that we've talked a little bit about metrics, right, usually the next step is connections. In Riemannian geometry, there's a unique torsion-free metric-compatible connection. Okay, torsion-free and metric-compatible are the two most natural requirements. You want to agree with the smooth structure, which is the Lie bracket, and you want to agree with the orthogonal structure, right, G. In Hermitian geometry, because we're working with holomorphic structures, torsion-free is not the most natural thing to ask for anymore. So instead, we ask for some slightly other things. Okay. First off, we call a connection on the tangent bundle Hermitian if the complex structure is parallel. Okay. So this means that the connection plays well with the complex structure. The eigenbundle, right? This T10 of M, T10M, parallel transports into itself. Okay. If the connection is Hermitian. So this is really relevant. So it plays nicely with the complex structure. We call a Hermitian connection Chern if its torsion has no 1-1 part. There's another definition of Chern connection that we'll use later on holomorphic vector bundles. But basically, when you let the Chern connection act on a vector, and you plug in one of these vector fields that's like a -I eigenvector of J, the Chern connection acts like the del bar operator. Okay, so that's this. Torsion-free isn't the most natural thing to ask for, but agreeing with the del bar operator is. Okay, that's agreeing with the holomorphic structure. A lot of books will call it that. And then the Bismuth connection, it doesn't really super have an extension to like holomorphic vector bundles. It is typically just defined in terms of its torsion, right? So a connection is called Bismuth if its torsion can be lowered to a totally antisymmetric 3 form. And there are some useful results about this, right? It can be shown that the Chern and Bismuth connection are unique when G is pluriclosed, basically the same way you show the Levi-Civita connection is unique. And the torsions for both of these connections depend on del omega, right? They're like linear in del omega. Yeah. So it becomes pretty clear that when d omega vanishes, the Chern and Bismuth connections, they collapse back into Levi-Civita. And Godeshan showed in 97 that on pluriclosed manifolds, there's one parameter family of Hermitian connections, but that one parameter family is uniquely determined by the Chern and the Bismuth. Okay, so in some sense, like where you have one connection in Riemannian geometry or Kähler geometry, you have two in Hermitian geometry. Okay. Really, there's a line, but it's determined by the two. So we've talked about connections. The natural thing after that is curvature. So in Riemannian geometry, the curvature tensor of the Levi-Civita connection has like 3 algebraic symmetries. It's antisymmetric in the first 2. It's symmetric with respect to swapping pairs. And you have this algebraic Bianchi identity. So, I mean, that's about 3 algebraic symmetries, depending on how you count. But in Hermitian geometry, we're not talking about the Levi-Civita connection anymore. All right, we're not torsion-free. So we have some slight changes to some of these symmetries. We also have a complex structure floating around, which reintroduces some symmetries. So let's talk about curvatures. If we're on a pluriclosed manifold, MJG, then omega with a superscript C and omega with a superscript B are the curvatures of the Chern and Bismuth connections. Okay, I'm not going totally into my sign conventions right now. I'll probably be doing that later. But this is pretty standard. Okay, you define it the standard way. And you can notice that, so I'm talking about the curvature endomorphisms here. But if you lower that last index, then the 4-0, or like the 4 lower index curvature, lives in the space wedge 1-1 tensor wedge 1-1. Okay, so that means for the Chern curvature, when all four indices are down, it's like unbarred, barred, unbarred, barred, and you can swap within the pairs and get a minus sign. Okay, but you can't swap between the pairs. And then the Bismuth connection, or the Bismuth curvature, is even different, right? That lives in wedge 2, tensor wedge 1, 1. I should say the complexified wedge 2, really. But so your first two indices can come in any combination of barred and unbarred. And you can swap them for a minus sign, but your last two indices are always unbarred, barred. You can swap them at the cost of a minus sign. Okay, so there's combinatorially, the Bismuth connection is a little more difficult to work with, just because it has more non-vanishing components. We can also define the first Ricci curvature. Let me point at these while I'm talking about them. We can also define the first Ricci curvature, which is this guy, and the first Bismuth curvature. All right. This is why I wanted to give you the curvatures as endomorphisms, because then there's a natural trace. Okay. So you trace over the endomorphism part, and you're left with a 2 form. Right. In particular, it's a wedge 1, 1 form. And row B, right, you're left with a 2 form. And then something that's especially relevant for us is the second Chern-Ricci curvature. Okay, this tends to be a guy that pops up a lot for us. This is the omega trace. Okay, so what we're actually left with is the endomorphism part of the curvature. Okay, we trace the first two, you're left with the endomorphism part, and you get an endomorphism. All right. Oh, let me see if I can go back to clicking. There we go. Something akin to a Bianchi identity hold for both of these guys, but they're a little complicated because our connections aren't torsion-free. Okay, so the easiest one is for the Chern connection, and you're just left with the covariant derivative of the Chern torsion. Okay, so something else to keep in mind is that these notions of curvature aren't completely unrelated, right? I always end up citing Ivanov and Papadopoulos for this, but I have a feeling that, I mean, even people back as far as the 80s understood that there was relations between these notions of curvature, but one of the first relationships I saw between them was this one, right? So the difference between the first Ricci curvatures of each of these connections is dd star omega. The next thing I want to talk about a little bit is just Bismut-flat manifolds, and in particular the Hopf surface. Why am I talking about the Hopf surface? Well, the Hopf surface is, in some sense, the simplest, non-trivial Bismut-flat manifold. Okay, I'll talk a little bit more about that in a second, but I figure first we should define Hopf surfaces. So the place to start, we take two non-zero complex numbers whose moduli are smaller than 1, and we define a z action, okay, on this C2 without the origin, whose generator is just this f right here, okay? You just scale each component separately. The nice thing about this is that it's holomorphic, it's like properly discontinuous, all of this jazz. We can just apply the quotient manifold theorem, and we end up with m alpha beta. Okay, m alpha beta, this quotient of C2 by our z action, is a Hopf surface. Okay, a lot of times you'll see these called primary Hopf surfaces, and secondary Hopf surfaces are coverings of these guys, but I won't really talk about that. Something interesting is that these are all diffeomorphic to S3 cross S1. And they do not admit Kähler metrics because they are S3 cross S1. You can check. They're not symplectic because the second Betti number, right, the dimension of the second cohomology vanishes. Right? You can do that by the Knuth formula. And when alpha and beta have the same norm, we call the Hopf surface diagonal. Sometimes you'll see it called isosceles or standard. But we'll call it diagonal because I believe that's what we do in the paper. All right. So, the first place. So, just because this is a differential geometry talk, I figure it's worth throwing in a couple ugly calculations just in case you're not familiar with Hermitian geometry. And so the one that I really wanted to do is just checking that the Hopf surface, the diagonal Hopf surface, is in fact Bismut-flat. So the first thing we do is we define like an F invariant metric on C2. Okay, it has this Kähler form that I've written here. Right, I've got this Kähler form right here. This is F invariant. If you pull back by our generator, the metric stays the same. Okay, and what that means is this Kähler form descends through the quotient map. So it defines a nice metric on the Hopf surface. And because our quotient map is like a nice covering map, we can really just work with coordinate patches on the Hopf manifold like they live in C2. Then I mentioned before that you can compute the connection coefficients for the Chern connection. It proceeds basically this way. It's very similar to the way you would do it for the Kozol formula. And repeating this the necessary number of times, you end up with these connection coefficients. Right, so something worth noticing is that there's not, so if you take the connection derivative of del omega, or of del w, right, there's not a del z component to that. Yeah, and you can also see this is clearly not torsion free, because if you swap z and w, you don't get this guy again. All right, we can also compute the Chern torsion, right? Just by taking these antisymmetric combinations of Christoffel symbols, okay, and then lowering them by the metric, and we just end up with these fellows here. Okay, these are the only non-zero ones up to antisymmetry in the first two indices. And then, this is kind of a side note, but the Bismut connection can then be completely specified by these connection coefficients and a Leibniz formula. And just because the Bismut curvature tends to be a little more difficult to work with, just combinatorially, we actually work from the Chern curvature. I'm going to go ahead and list the components below. You can compute these out kind of the standard way. I guess just to clarify sign conventions, it's worth mentioning that so omega A, B, C, D for me is G of the commutator of the connection in question, and then the upper index gets lowered to the end. Okay, so I mean, for example, like this is the Chern. Okay, Bismut works pretty similarly. is the same sign convention. I just figured that's worth mentioning, right? And this, again, this only works for coordinate vector fields, right? Because technically there should be like an extra term with like the commutator, okay? In general, right? So using that formula and that sign convention, this is what we end up with, all right? Which is pretty handy. But you'll notice that we've got this guy looks an awful lot like this guy, which is precisely what goes in here. I mean, not to spoil the punchline or anything, so I already kind of said it. The curvature ends up being 0, right? You can already see that the 1, 1 part, the 1, 1 tensor 1, 1 part is pretty obviously 0. This 3, 1 part is a little trickier, but you can check it just by using the Leibniz rule on the Chern connection applied to the specific torsion components that we wrote before. All right. Now we can say that this is the simplest non-trivial, but still fairly generic because of a classification result by Wang, Yang, and Zhang. So in the case n = 2 in complex surfaces, every Bismut-flat manifold is either Kähler and flat, right? Flat without a descriptor is unambiguous in the Kähler setting. It's just Levi-Civita. Or, if G is non-Kähler, it has to be a constant multiple of the standard metric on a diagonal Hopf surface. Okay? So the diagonal Hopf surface with the standard metric is the most general Bismuth-flat manifold in the surface case. All right. When you get to n = 3, the classification is still fairly concrete. If you're talking about a simply connected Bismuth-flat non-Kähler manifold, then that manifold has to be holomorphically isometric to either a Calabi-Yau threefold or C2 without the origin, tensor C. Okay, and the metrics on those are like a particular kind of bi-invariant metric on the Calabi-Yau, or a Hopf metric and a flat metric product on the C2 without the origin times C. Yeah. So again, right, the Hopf surface, it's about the simplest non-trivial non-Kähler manifold, but it's also fairly general because every Bismuth-flat surface is a diagonal Hopf surface. All right. The next thing to talk about are pluriclosed metrics and holomorphic Courant algebroids. These are a little new, so I think it's worth going over some definitions. An exact holomorphic Courant algebroid is a type of holomorphic vector bundle, really. It's got a bracket and a projection map satisfying some axioms. But I really want to specify things down and just give you the definition that is most relevant to us and really covers everything up to isomorphism. So, given a complex manifold and a 3-0-2-1 form, which is closed, we can define a Courant algebroid as T plus T star with extra data, right? With a twisted del bar operator, this bracket, an inner product, a bracket, and an anchor map. The del bar is defined this way, right? We just hook xn to the 2-1 part of tau. The neutral inner product is just exactly what you would expect it to be. The bracket is the Lie bracket up to some extra terms, which are relevant And then this pi is called the anchor map. Okay. Something to notice is that this is technically not a Hermitian bundle. Our co-author called it an orthogonal bundle, just because this neutral inner product is not positive definite, right? It's got a funny signature to it. Typically speaking, we'll be taking tau to be 2i del omega, which is related to the Chern torsion. That 2 will come and go just by normalizing omega differently. And those pieces of cohomological data are relevant because they're related to different notions of isomorphism of Courant algebroids, right? Or different notions of equivalence of Courant algebroids. Okay, if you think about isomorphisms in terms of isomorphisms as a Courant algebroid, then the Epley class of omega is what you're looking for. But if you're just thinking of Courant algebroids as isomorphic up to isomorphisms of holomorphic orthogonal vector bundles, then you really only need the torsion class. More details given in generalized Ricci flow by Garcia Fernandez and Streets. I believe you can find it on the archive now, actually. So we're geometers, right? We care a lot about vector bundles. We also care a lot about metrics on vector bundles. So how do we put a generalized metric on a holomorphic Courant algebroid, right? Well, a generalized metric on a holomorphic Courant algebroid is a Hermitian metric on t plus t star of a particular form. Okay, you can see here, right, on tangent vectors it acts like G plus G inverse on this beta form, right? This mixed part, first you hook x into beta, and then you take the inner product with xi and multiply by I and take twice the real part. And then you use G inverse on the t star part. Now, the thing that's especially relevant to keep in mind is that there is an integrability condition here. Okay, we have that T naught, we need T naught minus del omega to be d beta, right? So this is kind of saying that T naught and the 2i del omega Courant algebroids are related by a beta transformation. Okay. In practice, we can loosen this a little bit. We only really need this relationship here. We need tau naught minus del omega as del bar beta, which corresponds to a loosening of the equivalence. Okay, we don't really talk about isomorphic as Courant algebroids. We talk about isomorphic as holomorphic orthogonal bundles. And again, refer to generalized Ricci flow for the more general picture. It was pointed out to me before that calling these generalized Hermitian metrics seems a little weird without an understanding of what's going on behind the scenes. All right. So we've talked a little bit about Courant algebroids and how they come from Pluriclosed metrics. Something else that these Courant algebroids let us do is have a cleaner perspective on some classical identities. So in a 1989 paper, Bismuth proved a relationship between the Chern curvature on this T plus T star with a specific holomorphic structure, and the Bismuth curvature of the complexified tangent bundle. Okay, we restated and reproved that in terms of holomorphic Courant algebroids. So we start on a pluriclosed manifold with a pluriclosed metric and a 2 form, right? A 2-0 form with this condition here, right? From this, we can define the I del omega Courant algebroid, right? We dropped the 2 because we renormalized the metrics. and we define a generalized metric, capital G, but with no beta, right? The reason there is no beta is because we're working on this on the omega Courant algebroid and not the omega naught one. Okay, if we pull everything back to the omega naught one, the beta shows back up. All right, so this theorem of Bismuth, we can kind of work through it a little bit. The first thing that gets shown is that there's a particular isomorphism between these smooth vector bundles, right? The complexified tangent bundle and t plus t star here, given fairly simply just by this, right? You really just kind of flip t01 if you think about it. That isomorphism has some more special properties, okay? We can define a particular Hermitian connection on the complexified tangent bundle, right? We call this the minus connection, okay? It's related to the Bismuth connection, but instead of adding a torsion term, we subtract a torsion term. This guy defines a holomorphic structure on the complexified tangent bundle by its 0,1 part, right? It's not the standard d bar operator, but it defines a new d bar operator on the complexified tangent bundle viewed as a holomorphic bundle. Okay, holomorphic vector bundle. And with this holomorphic structure, psi g becomes a holomorphic isometry. Okay, the map becomes holomorphic with respect to the holomorphic structures on each of these bundles, and it preserves the metric. And because of that, right, because it's a holomorphic isometry, it preserves the connection, right? Churn connections pull back to churn connections. That's why this choice of Dolbeau operator was so important, right? That forces the minus connection to be churn. And then the pullback of the churn curvature is going to be the churn curvature. Okay, so it's kind of smart alecky, but it's really nice. I mean, it's very beautiful. So we have this relationship between curvatures downstairs and curvatures upstairs. Curvatures on the complexified tangent bundle and curvatures on the holomorphic Courant algebroid. We can also do this in terms of coordinates, which is pretty nice. So if we take a holomorphic coordinate chart, Zi, and then we have the following identities. And again, so t squared is this guy. The 1,1 tensor 1,1 part of the Bismuth tensor, Bismuth curvature tensor, is just given this way, right? You apply this missing symmetry from the Riemannian curvature tensor to go from Bismuth to churn, right? This is the churn on the complexified tangent bundle minus t squared, right? Something that's quadratic in the torsion. For the 2,0 tensor 1,1 part of the Bismuth curvature, it's really just the churn connection covariant derivative of the churn torsion. All right. This, we mentioned it before, but yeah. And just to reiterate, this is the churn connection for little g on the complexified tangent bundle. So then finally, you can cobble all of this together to see precisely how the churn curvature on the holomorphic vector bundle composes with the, or is related to the Bismuth connection on the complexified tangent bundle. Okay, I'm writing this as like a linear operator. So if you put tangent plus cotangent here, then this part eats the tangent and spits out a tangent. This part eats the cotangent, spits out a tangent. All right, just to clarify. And the reason we're composing with these exponential maps is because this identity actually holds on that omega 0 Courant algebroid, right? The background algebroid, which complicates some identities, but it lets us talk about an unevolving algebroid when we start talking about algebroids evolving. Okay. All right, that's it for the first part. We'll move on to the second part here in a minute. I had wanted to do some of these calculations, but they're kind of grinds. You can find them in the paper.